Good morning. So I will talk about the role of mutual friction in superfluid helium turbulence. And it's a work done in collaboration with Juan Polanco, who used to be in Lyon, but he's now a CNRS researcher in Grenoble. And also with Luminitsa and Yonut Danaila and then Tong Sang at the University of Rouen, and Philippe Roche from Grenoble. And this work has been done in the context of the CUTE HPC project, which is a project funded by the French National Agency. So to give you the outline of this talk, so first I will give a brief introduction of superfluid helium, recalling the main features. And then I will talk about quantum turbulence under the so-called HVBK closure condition. So let's start with the introduction. So liquid helium at temperature below the 2.17 Kelvin undergoes a transition and becomes becomes superfluid. And superfluid helium is not a perfect Euler fluid with vanishing viscosity, but behaves as it is made of two components, an intimate mixture of two co-penetrating fluids. One fluid is the superfluid component, which is inviscid, and which has vorticity, which is confined to line, and with atoms in quantum ground state. And the other component is the normal fluid components with atoms in excited states, and it behaves as a classical Newtonian fluid. And the two components are coupled. And in this study, an important feature is that the mass density of these two components depends on the temperature. When the temperature is just below the transition, you have normal fluid and very little superfluid. And when the temperature decreases, you have an increase of the mass density of the superfluid in the system. And in this study, we will be interested in the range of temperature, typically between 1K and the transition, where you have the coexistence of the two components and strong interaction between these two components. Oh, shit. Okay, just to give you a rough idea of the length scales in the problem. The size of the quantized vortices of the superfluid components is the core is typically of the order of the angstrom. These vortices, they undergo Kelvin wave vortex reconnections, so processes at scale between typically the nanometer and the micrometer. The typical distance between the quantized vortices is the micrometers or tens, hundreds of micrometers. And in the following, we will adopt a coarse-grained representation of the dynamics. So we will consider a resolution which is large compared to the intervortex distance. And we do that to describe flow at size from millimeters and beyond. So we are interested in the coarse-grained dynamics of superfluid helium at temperature between typically 1K and the transition temperature, when you have these two components. And so it's coarse-grained dynamics, so it means the resolution of the dynamics is at a scale which is much larger than the intervortex distance. And we model the dynamics of the vortex tangle by an Euler fluid. And we have to add to this inviscid Euler fluid some subgrid scale dissipation process related to vortex reconnection, Kelvin waves, etc. For the normal fluid components, we consider the normal fluid is driven by the Navier-Stokes equations with some kinematic viscosity. And the two components are coupled with a mutual coupling. Okay. For the coupling, we use so-called HVBK closure condition. And so what does it mean? The physical model behind this closure condition is to consider superfluid helium as an isothermal and incompressible fluid. And we consider coarse-grained dynamics so that the superfluid velocity field is supposed to be smooth. It's supposed to be smooth so we can define a superfluid vorticity. And we consider that this superfluid vorticity accounts for the underlying tangles of quantized vortices. So in terms of equation, so we recognize the Navier-Stokes equation for the normal fluid components with this coupling force here. And for the superfluid components, we get the Euler equations and the opposite of this coupling force and a term for subgroup dissipation. And the HVBK closure conditions gives an expression for this coupling force. And it tells that it depends on the mass density of the two components, on the superfluid vorticity, which accounts for the underlying quantized vortices. It depends on the slip velocity, the velocity difference between the two components, and some empirical parameters. And it is made of several terms. A terms of mutual friction between the two components, which is a dissipative term. A term of, so it's a kinematic term of Magnus effect, and plus additional terms related to vortex distortion. But in the framework of quantum turbulence and in the range of temperature, we consider where the two components coexist. I mean, we can claim that the most relevant term is a friction term, and so we just keep this term in the modeling. Okay, so I would like to make just a remark about HVBK closure condition, which can be discussed. So HVBK was originally designed for regular patterns of quantized vortices with parallel orientation, with the vorticity giving the information on the vortex line density. So in the context of quantum turbulence, this closure condition is expected to capture only the locally polarized contribution of the superfluid vortex tangle. So it means also that randomly oriented quantized vortices which participate to the mutual friction are not taken into account. So this is a clear limitation of the modeling. So we can mention that there are alternatives to the HVBK closure condition, and for example, the Vinance model. And the Vinance model takes an opposite perspective and accounts for the locally non-parallelized superfluid vortex tangle. And so here, instead of having the vortex line density of the polarized vortex, you have the vortex line density of the unparallelized vortices. And Vinance proposed an additional evolution equation for this density, which is essentially the balance between a production term and a decay term. And of course, the best would be a combination of the two to take into account both the polarized and unpolarized contributions. And so, I mean, we can mention that there are attempts to unify Vinance model and the HVBK closure condition, in particular by introducing some measure of local anisotropy and to use this measure to parameterize the coupling force. Okay, so now I will go to quantum turbulence. So the mainstream consensus of quantum turbulence is that it's probably very similar to classical turbulence. And of course, the questions are to what extent. So how does it compare, quantum turbulence and classical turbulence, scale by scale? And also, does this similarity or possible differences depend on the temperature? So in the context of turbulence, in quantum turbulence, you have three ingredients. So the nonlinearities, the triadic interaction, which are responsible for the energy cascade, the viscous dissipation related to the normal fluid components, and also for, the artificial viscosity of the superfluid components. And you have a third ingredient, which is very important, which is mutual friction. So the issue is to understand how these three arguments play together. Okay, so to clarify the equations we will use. So there is no temperature effect, and for the normal fluid, so we have a Navier-Stokes equations in compressibility conditions, then the coupling force. For the superfluid, we will use the Navier-Stokes equations by assuming that the subgrid scale dissipation process can be modeled by kinematic viscosity. And here we have the coupling force, and it's incompressible also. And for this coupling force, we use the HVBK modeling, which has this very simple form, which is proportional to the modulus of the superfluid vorticity and proportional to the slip velocity between the two components. Okay, and in the analytical developments, we will use a simplified force, simplified form of this equation by assuming that this term is almost constant in the flow. So it's kind of a mean field approximation. Okay, so first let's start with a wave number by wave number of energy budget of quantum turbulence. And in the situation, typically a temperature of 1.96 Kelvin, where you have an equal proportion of superfluid and normal fluid. And here I show the energy budget. The blue line is the energy flux. The yellow line is viscous dissipation. And the green line is mutual friction. And so we see that the effect for these two components individually, there is a strong effect of mutual friction on the kinetics. And we get in particular that for the superfluid, mutual friction is a loss of energy. So by mutual friction, superfluid lost energy. And this energy, you get it here, so it's gained by the normal fluid and eventually dissipated by the normal fluid. But what is interesting is that when you consider the overall budget for the mixture of the two components, the dissipation by mutual friction is almost zero, except at very small scales in the dissipacy range. So it means that mutual friction takes energy from the superfluid and gives this exact amount of energy to the normal fluid, at least in the inertial range, in the cascade range. And this exchange is responsible for the locking of the two fluids such that the slip velocity is zero and there is no friction dissipation. And of course, this mechanism is not possible at all scales. And eventually, at very small scales, you have an unlocking of the two fluids and some dissipation by mutual friction. So the first message is that mutual friction is responsible for transfer of energy between the two components, such that the two fluids gets locked in the cascade range. Okay, and I mean, you can do the same at different temperature, and you always get the same conclusion. And dissipation by mutual friction is almost zero, and is just non-zero in the at very small scales in the dissipative range, which means that mutual friction is essentially an additional viscous process in the business at very small scales.
The typical intervortex distance at which K corresponds in those solutions, more or less. Just to give a reference, a physical reference to the scale of K.
The K is a wave number, so it's from numerical simulations.
It is not resolved.
Should be up to the right.
Yes. It is multiplied.
Okay, it's always HPBK simulation.
Yes.
It doesn't
Yeah.
go to any beyond HPBK.
Yeah.
But for consistency, from the superfluidicity, you should recover what is the intervortex spacing and put the market there for consistency.
Excuse me? I cannot hear you.
From the superfluid vorticity
Yes.
calculated by HBK, you should recover the intervortex distance and check that it is
Oh, the intervortex distance is it's typically of the order of the cutoff of the spectral simulation. It's from pseudo-spectral simulations of the system.
So basically the cutoff is at the intervortex distance.
Yeah, yes, it's here. Okay, so
Sorry, but then if the cutoff is at the average intervortex distance is at the cutoff, so at the largest K, then the superfluid dissipation kicks in like 2 orders of magnitude earlier. So this is something which probably, I mean, if I have to look to this, and I would say that the average intervortex distance is almost around 100 when the cascade is the transfer of energy goes to 0, and then the superfluid dissipation starts to kick in if the superfluid dissipation accounts for small effects.
okay. Sure.
I think by consistency, as you are adding viscosity to the superfluid component, you have the Kolmogorov length or the Taylor microscale. That was a discussion of last week. Whatever these two correspond to the vortex distance is fixed by your viscosity. So I think if we look at this model, we should not look at the small scales and concentrate as you are doing in the inertial range. And the intervortex distance should be more or less where eta
I mean,
is.
I will discuss that afterwards.
I have one last question of order of magnitude. So there is a ratio rho s over rho n above which, you know, this description somehow breaks down, and all the dissipation is coming from Kelvin wave starting with music length probably. So my question is, do you have an order of magnitude at which value of rho s over rho n you should drop this kind of description and say it's different?
Oh, it's yes. Actually, we did not investigate the whole range of possible mass density ratio, but typically also we made tests with the ratio of the order of 50, and it was. I mean, this picture was still valid. I mean, yes, but at some point you have to give up the coarse grain dynamics description and go to some quantum mechanics and.
The order of rho n over rho s where you have to drop Navier-Stokes for
But I said it's for temperature between typically 1K and the transition.
Just in interest, I want to answer Mark's question. We are very, this is said by at least one order of magnitude. And the indication is when you look at the effective viscosity, which has been measured down to low temperature, there is a continuous curve, and at some point it kind of saturates, and there's a change. And if you look at this change, it's typically 1K. 1K is typically a ratio of 1,000 to 100.
Yeah.
So this is
Okay, so now I will switch to some analytical results. So I want to recall a famous statistical equations we can get in classical turbulence, which is the Kolmogorov four-fifths law. And so under the assumption of stationary homogeneous isotropic turbulence, one can establish an exact scale-by-scale energy budget from the Navier-Stokes equations. And this budget tells first that what is injected is dissipated in mean. So the dissipation rate is equal to the injection rate. And you get a statistical equations telling that the third order structure function for the velocity increments over a distance r is scales linearly with a special increment r, and this is the signature of the energy cascade, and you have to add some viscous term to take into account viscous dissipations. And so these equations can be reformulated to get the famous Kolmogorov four-fifths law. So in the context of quantum turbulence, you can do the same with your Navier-Stokes, two Navier-Stokes coupled two Navier-Stokes system. And so individually for each component, for the normal fluid, so you get that first what you inject in the normal fluid is dissipated by the viscosity of the normal fluid, and there is a loss of energy by mutual friction. And the statistical law is the same as previously, and you have an additional term which accounts for the mutual friction. And you can do the same for the superfluid. What you inject, energy injected in the superfluid is dissipated by the artificial viscosity of the superfluid. And also there is a loss due to mutual friction, and you get a similar equation with this term for mutual friction. But what is interesting is to combine these two equations and to write a statistical equation for the mixture. And when you do this combination, and you are able to write a four-fifths law for superfluid helium, for the mixture of superfluid helium, which has a flavor of the four-fifths law for classical turbulence, and you have this additional term which is related to the mutual friction. And this budget can be interpreted as a mass density weighted scale-by-scale budget of superfluid helium. And so the question is to characterize this supplementary term compared to classical turbulence, and to see at which scale it is effective. So this term, for the moment, the coupling force is just F, and you can say more precisely what you put in F. So if you use the HVBK closure condition, you have this expression for the coupling force, and you can use this mean field approximation, so you get that the additional term in the energy budget as this form, where you see here the correlation function of the slip velocity. And from numerical simulations, you can plot this term as a function of the scale. And what you see is that in the limit of vanishing scale, this term scales like the special increment r, which is recovered by the simulations. But when you increase the scale, you get a strong depletion of this term, and the amplitude of this term remains much smaller than this transfer term, which means in the budget that the additional terms related to mutual friction is always negligible to the cascade term in the budget. So we recover the previous observation that mutual friction in terms of energy budget is negligible in the cascade range. Okay, and So if mutual friction for the mixture is just an additional dissipation process, you can reformulate or extend the definition of the Kolmogorov scales by accounting by this additional dissipation. And so just to remind how the Kolmogorov scale is obtained in classical turbulence, and in the dissipative range, the velocity field is regular, and the second order structure function can be approximated from the local gradient. So you get this estimate of the structure function as a function of R. And in the inertial range, the velocity field is irregular, and from the Kolmogorov or dimensional arguments, you get this behavior, and when you match the two, you get the Kolmogorov scale, and with this expression. So in the present framework, you can do the same, and so you match the second order structure function of your velocity field, and you get this estimate, and you match it with the estimation of the structure function in the inertial range, which is given by the classical expression. And when you match the two, what you get is you recover the Kolmogorov expression, and you have an additional term which accounts for the fact that you have an additional dissipation process which is due to mutual friction. So you can extend in this framework the definition of the Kolmogorov scale by accounting for mutual friction dissipation. And if you have this extended viscosity, then you can define an extended Reynolds number, and you get this formula, and you can also introduce Taylor Reynolds number the same way. And now if you do the simulations and you use these characteristic scales to rescale the scales, so we do simulations at different temperature, and we plot essentially the energy budget as a function of the scale, normalized by the new Kolmogorov scale. And what you see is that all the temperature, all the scales, they collapse, and you only see difference in the dissipation range when you have strong effect of the temperature. Depending on the temperature, you get different curves, and also it depends on what you put for the superfluid viscosity and the closure conditions you use, of course. And just the last 5 minutes, I will say some words about some controversy on intermittency in quantum turbulence. And you have some results in contradiction. So first, experimental studies, and the first measurements of intermittency in superfluid helium is due to Moran Tablin in 1998. And they found at that time that at temperature equal to 1.4 K, and that the scaling exponents of the velocity structure functions are very similar to the scaling exponents we get for classical turbulence. And more recently, an investigation of intermittency has been done for several temperatures in Grenoble, and so they measured again the scaling exponents of the structure functions, and they found that for all the temperature, I mean, they coincide with the scaling exponents of classical turbulence. But more recently, you have some new experimental results where they find that there is a dependence of intermittency with temperature, and in particular that you have an increase of intermittency at temperature close to 1.85 Kelvin, where the two components are in equal proportion. So that's from experimental study, and numerical studies fuel this confusion by adding results where they find, I would say, strong dependence of intermittency with the temperature, but with results in contradiction with each other. And in particular, we have this first set of results where they find an increase of intermittency, and another set of results where they find a decrease of intermittency. So there is a lot of confusion about intermittency in quantum turbulence and whether it depends or not on the temperature. So in our study, so we computed the flatness of the velocity increments as a function of the scale for the two components from numerical simulation, and for different temperature, and by using this, by rescaling the length scale, we are able to show that all the flatness they collapse on a unique curve in the inertial range, and the result is very comparable with what you get for classical turbulence, which is the black line. But when you reach the scales where dissipation comes into play, and dissipation is viscous dissipation plus mutual friction, and then you get a span of the results. So our conclusion is that in the inertial range, in the cascade range, you have universality, and universality is the same as classical turbulence. But when dissipative processes come into play, and then you lose this universality, and it depends on in particular on the temperature. So what we suspect from this very different result is that the range over which the scaling exponents have been measured is not exactly an inertial range, but it's a mix of dissipative and inertial range. So that's why it depends on the temperature. And it's quite clear from in particular in these publications where we see that the scaling exponents have been measured in this range, which is clearly under the effect of dissipative processes. So it depends on the temperature. Yes, and they use standard self-similarity, so everything is hidden behind representation. Okay. So I'm done, just with my conclusions. So the conclusion is that mutual friction for the mixture of superfluid helium is essentially a dissipative process that adds to viscous dissipation at very small scale. And this allows us to define an effective Kolmogorov scale, which is an extension of the classical Kolmogorov scale that accounts for the mutual friction dissipation. And from this Kolmogorov scale, we can define an effective Reynolds number. And the second message is in the inertial range, in the cascade range. The cascade remains the dominant dynamical process. The two fluid components are locked, and the scaling exponents agree with that of classical turbulence for all temperature. We don't see any temperature effect. Okay, thank you.
Okay, we've got special dispensation from the organisers to shift the coffee break slightly later, so the
to zero when you're very close to T lambda, where beta prime becomes of the same order of beta in the mutual friction parameters?
What do you mean? Do you mean if
At your very high temperature, where T is close to T lambda, the two mutual friction parameters become of the same order of
Yes.
magnitude, but you neglect beta prime. Is that appropriate, or could there be a slightly different regime of turbulence there?
yes, qualitatively, we don't expect some big change by just adding this B prime term. I mean, what?
I didn't mean to open a can of worms.
But in practice, we didn't play with the value of the empirical parameter with the temperature, and so we kept them constant for in all conditions.
Do you want to respond to it?
Yeah, I would like just to add something that really goes in the same direction as you. With Nico, we look at the intermittency in a HVK model in a slightly simpler version of yours. So yes, mutual friction was the mean entropy. And we did vary the new S, the superfluid, as a function of temperature. And we didn't observe any trace of
we did
change on the intermittency.
Yes, we did it also. And actually, qualitatively, it's, I mean, you don't expect big change by playing with the value of the parameters, B prime.
We didn't see any trace of change, of any change of intermittency on all range of temperature we studied.
What about if you change the shape of the... Because you took the viscosity for the superfluid, you took a classical Laplacian law. But you could take, what about if you take, for example, a Laplacian to a power that is equal to 2/3 or something?
We did something like
Hyperviscosity.
this, and even we removed the dissipation term for the superfluid, and we just imposed a spectral cutoff, which is like an infinite hyperviscosity, and so you get some. I mean, some thermalization zone near the cutoff, which plays the role of dissipation, and but we get exactly the same results. So even changing the form of the dissipation process for the superfluid does not change the picture. It changes the value, but not the picture. Okay, a special shape.
One last question from Carlo, and then we'll move on.
In the initial slides, it was mentioned vortex tension, but then it disappeared from the equations.
Yeah. In the HVBK force, right? Here. Yes.
In the equation, in the original HVBK equation, there is what is called the vortex tension term, which is the omega s unit vector crossed with the curl of omega s.
Yeah. But you don't. Do you expect this term to be significant in the context of quantum turbulence?
Well, the question is...
I mean, we made paper together and we ignore this term, right?
Okay, let's leave it there because there's plenty of time in the coffee break to discuss, and let's thank Emmanuel again.